Okay, good afternoon. My name is Alessandro Barbieri at Pluribus Networks. I'm responsible for product management. And today, I'm going to talk about the value that a network switching fabric can add to an environment where you're deploying Kubernetes applications. So now you have bought your OCP switches, you're ready to build your fabric and to support containerized applications. So what is the role of the network at least from a visibility and observability point of view? What kind of value add can you offer? So this talk is describing Pluribus Networks' approach, but it can be very well abstracted and brought to other networking solutions. So I'm going to spend a few minutes to just level set on some language for Kubernetes, so it's easier also to follow the rest of the presentation. So I'm going to spend a few minutes here to hopefully not to bore anyone, but to describe what Kubernetes is and what Kubernetes does. So the same language will level set and will let us follow the rest of the presentation. So Kubernetes this is the definition. If you open the website, Kubernetes.io, is a portable, extensible platform for managing containerized workloads, right? And it does multiple things. One is there is a declarative configuration and automation sort of framework. You declare the state of an application, and then Kubernetes takes care of converging the actual state to the desired state. You describe how many replicas, how many pods, how many containers you want to deploy, and in a sort of a control loop type of application, Kubernetes always guarantees that the end state you're declaring is actually achieved. It's the ultimate intent-based networking sort of scheme, if you will, but for the entire infrastructure. One of the most interesting aspects of Kubernetes is the way it manages traffic and forwarding and east-west traffic between containers or pods, as they're called in Kubernetes. There's a lot of traffic distribution. There's a lot of load balancing, a lot of forwarding, rewriting of packets for east-west traffic. We're going to just take a quick glimpse of it in the next couple of slides. But it's very complicated how networking is actually distributed across all the Kubernetes nodes and all the Kubernetes pods, managed containers. There's a lot of magic in the networking. In fact, actually, networking is extremely, I think it's extremely sophisticated overall. Kubernetes also offers very interesting self-healing capabilities. Like I said before, you declare the state of your application, and then through a control loop, Kubernetes is capable of actually achieving that state. So if a container dies, Kubernetes restarts the container. Also, Kubernetes manages the resources very effectively. There's a lot of intelligence and automation in how these containers are placed throughout the resources in the infrastructure based on their memory footprint, CPU footprint. And of course, the entire storage orchestration is also included in Kubernetes. So it's a full stack. It's a full stack platform, completely open source to manage containerized applications. All right, a few notions that are useful if you are a switching fabric, NetOps kind of administrator. You want to be aware of Kubernetes because those are actually the objects that you have to deal with in your network infrastructure. So number one, the smallest unit managed by Kubernetes is not called container. It's actually called a pod, right? A pod can consist of one or more containers, but a pod is what actually has an IP address, is an endpoint in your infrastructure. So in your switching fabric, the pods are what generates traffic, east-west or north-south. Each pod is given a unique IP address, so it's really an endpoint. And the complexity of containerized application is that they're distributed in microservices, and then each microservice that can scale horizontally into multiple pods. So there's an explosion of number of endpoints and IP addresses in a Kubernetes application. The elegance of Kubernetes forwarding is that you never talk to a pod directly, an endpoint. You always talk to a service. A service is a level of indirection, it's sort of a proxy. You can see it here in the picture. Right? You have service with an IP address 1.1.1.1, and behind this service, you have multiple pods 10, 10, 10, 1, 2, 3, and 5 for a particular application labeled application A. And the way traffic reaches the pods, you speak to a service, right, which is this proxy effectively, and then there's a load balancing operation, right, happening within the Kubernetes cluster. This generates most of the east-west traffic. So think of it as a gigantic distributed load balancer. That's another way of looking at it in simple terms to Kubernetes. And once you have all these pods and applications, they're organized in replica sets, which are effectively Kubernetes objects which describe the identical replicas of a particular pod, which contain one or more containers, and then they're organized in deployments, which define all the characteristics of an application. There is a lot more. This is actually an oversimplification, but that's enough language and information to follow the rest of the presentation. All right, so what is really the problem here? You're deploying this gigantic distributed load balancer, which is really the Kubernetes cluster, right? You have a bunch of pods and application, and you're building your physical network, right? You have your OCP switches, you put your software on, and they really are like ships in the night, right? You have no idea really what's going on in the Kubernetes cluster. So everything is great, right? When everything is great, everybody's happy, but when something doesn't work, there's complete, you're completely blind to what's happening from the physical fabric and also from the DevOps Kubernetes environment. You don't know if it's a networking issue. So this is what we're trying to solve here, is provide the NetOps team enough tools to have an intelligent conversation with the DevOps team so they can triage and triangulate and root cause any problem in a Kubernetes application a lot faster. So what are the issues or the characteristics of Kubernetes application, which makes it a very challenging task? So containers come and go frequently. These pods I mentioned before, these atomic units of compute managed by Kubernetes, they come and go very frequently. So how can you really troubleshoot when something goes wrong, when something is actually long gone, right? You have no history, no memory, a problem occurred, these containers are destroyed, why things didn't work. So the short lifespan is a unique characteristics of a containerized and microservice-based application. This is another, the endpoint sprawl is another problem. I mentioned that before. Instead of having a monolithic application, now you're breaking your application into multiple components, and each of them is scaled into maybe tens or hundreds of pods behind it. So you can have an application that, for example, it's a web application, but in the back end, this application is supported by 10, 50, 100, or 1,000 pods, and they can scale elastically. So that you have a sprawl, an explosion of number of endpoints. And these endpoints are all distributed throughout your network, and you have no idea where they are. In a virtual machine environment, you know where vCenter is deploying a vSwitch, a VM, right? It's on a particular server, there's more control. Here, Kubernetes operates in a way that you have no idea how the workloads are distributed, you, the network administrator. So when something doesn't work, it's really a challenge to actually pinpoint where in the network the problem is. The third problem is the east-west load balancing, because now we're breaking an application into microservices and distributing these microservices. Now we have to distribute the traffic to these microservices. We have to load balance the traffic to all these sort of micro applications or micro pods supporting an application. So there's a lot of east-west traffic. Actually, I would say the vast majority of the traffic in a Kubernetes environment is east-west. So you really have no clue if you are, again, a NetOps or a network administrator, or really how to trace these application flows. You're speaking to the service I mentioned before, which is a proxy operation, and from that proxy, actually the traffic can go anywhere. And there are different load balancing strategies inside Kubernetes, but the point is that you have no control and you have no idea, right? So we want to think of how this fabric, based on OCP switches, can actually provide a little bit more value rather than raising your hand, I have no idea what's happening to your application. That's not the conversation you want to have. And last but not least, this traffic between pods and endpoints in Kubernetes is sometimes in the clear with an IP address and a VLAN, but more often than not is encapsulated. whether it's VXLAN, IP in IP. So it's really opaque to the rest of the network. You cannot necessarily, it's not that easy to just attach a sniffer and send the traffic to a probe, and you immediately see what's happening. First of all, there's way too much traffic to really accurately and comprehensively profile the traffic going through the physical network, but also now this traffic is encapsulated. So you only see typically the outer header, but the inner header, the conversation between the pods are really very hard to trace. So application performance, application availability is really a major challenge when deployed in a Kubernetes environment. Okay, so what do we do at Pluribus Networks, right? So we are building, I call it here, a Kubernetes-aware switch fabric, and you will understand where this awareness comes from. It's a lot simpler than it looks. But let me describe at high level the components, right? So we have OCP, ONI-based switches powered by Broadcom Merchant Silicon, right? We have a partner even here, Sesame IT Renew, that actually sells a full rack where our switch is at the top of the rack, but you can also buy an AI ML solution optimized for containerized workloads. But fundamentally, the hardware is OCP, OCP approved kind of switches, open networking switches. We can build a fabric with traditional, let's say, leaf spine protocols and tools, BGP and VXLAN. We have our own special sauce through our SDN fabric, but fundamentally it's a BGP fabric, layer 3 fabric for scalability and stability reasons, running a network overlay. We also have an SDN control plane, and this is actually where our solution starts to become Kubernetes aware, because this SDN control plane, which runs distributed in the physical switches, now talks to the API server for Kubernetes. So now we are aware, or we receive input or signals from the API server of every kind of deployment and pod running in the compute fabric, right? And because we have an end-to-end view thanks to the physical, to the SDN fabric, now we have full visibility of where all these pods and applications are deployed. We're not in the dark anymore. We know that on port 1, switch 1, and port 52, switch 52, this list of pod and applications are actually deployed. This is a very simple byproduct of connecting or subscribing to the API server. This is the same, is nothing fancy. When you join a node to a Kubernetes cluster, you need to effectively register with certain credential. We use the same file that the Kubernetes is using. We copy it on the switch, and then the switch talks Kubernetes. We could potentially also become a Kubernetes node, but there is no real use case. But the point I'm trying to make is we really are inside the Kubernetes cluster. But we just listen to this publisher-subscriber model with the API server, and we have full awareness and context of where all the workloads are deployed. And that's the starting point, right? So it's a simple idea, but because we have now this awareness of what's going on in the Kubernetes deployment, we can actually do things like locating specific application pods in the fabric. Here we've written a simple application called deployed through a deployment object called pet store, right? And with the command connectivity show, we can actually locate the different pods, right? Supporting this pet store application, and we can actually say or tell the user where they're connected. So worker 1 is a particular server, this is the NIC of the server, and this is connected to port 16, leaf 1 of our fabric. This other pod, QJ58S, is connected to worker 2, which is another Kubernetes node, the NIC, and then port 43 on the physical fabric. So we can really correlate the network events. Now we have at least the starting point to correlate events such as traffic spike, network congestion, with actually a specific application performance, right? Because now we identify where in the fabric are the bottlenecks, where in the fabric are the hotspots, and now they're correlated to particular Kubernetes applications. Another example is, let's say you are going through a fabric software upgrade, right? So through a software upgrade, you have to reload the fabric, and potentially, if your servers are single-homed, for example, you may go through an outage of a few minutes. Because you know where every application is deployed and distributed across the network, we have a command that allows us to determine the impact of, the impact of, my bad, this is actually the wrong command. But anyway, it's a KTS impact show. It tells you by reloading this switch which are the impacted applications, right? So this is actually a way to proactively negotiate and potentially alert the DevOps team or the application team, the cloud team, that as you are upgrading your application, those services may be impacted or affected in terms of application availability. Another example is, like I said before, all these pods are very ephemeral. They come and go very fast. Their lifespan is measured in minutes sometimes. So you want to have tools that allow you to track the changes that occur through the application, through the Kubernetes application environment. So we have, for example, this time machine, which is leveraging SSDs built on the switch. There is switch storage. So we preserve up to 24 hours of history regarding all the pods that have been added or removed. In this case, for example, we do pod show within the last 24 hours, and we notice that a new pod was updated, a new pod added, a new pod was updated. In the case, for example, there's an image refresh, and 2 pods got removed. So there is all the intelligence and granularity to go into the network and look between a particular point in time when, for example, an application outage occurred, what was the view from the fabric of the state of the Kubernetes application, right? So this is those are very simple tools, all coming from us, the fabric, being able to speak to or talk to the Kubernetes API server, and then preserving memory and state of the Kubernetes application lifecycle as they go through the churn and the lifecycle management from the Kubernetes controller. Another interesting capability we have is actually the ability, because there's a lot of east-west traffic, you want to be able to trace the potential paths, network paths that each pod or different pods take to talk to each other. So all this east-west traffic, sometimes there is congestion, sometimes there are outages. You're building a BGP fabric with ECMP and BFD and all these sort of efficient tools, but it's useful to trace the possible paths between any 2 Kubernetes container or pods. And with this command, KTS trace path, you identify the source pod and the destination pod. There can be a load balancer or can be a specific pod, and you have the list of potential paths through the fabric that this communication can take. So it's another very simple way to troubleshoot specific application performance issues, at least to have a starting point to have an intelligent conversation with the DevOps team. The most sophisticated capability, however, comes into be able to see the live traffic between containers being logged and the live flows being logged onto the network switch infrastructure. There are no extra probes that you need to deploy on the Kubernetes nodes. There are no extra, let's say, packet brokers or taps you need to deploy, none of that. You just use your switches, your OCP switches, and we'll build the software to take advantage of some of the Broadcom-specific offloads and table capabilities to really look and log into every connection, every flow between the Kubernetes pods. So in this case, we detect the presence of specific Kubernetes application. These 2 IP addresses belong to a specific Kubernetes application, hello world in this case. And then we can trace the connection between any particular endpoint in the Kubernetes application, in this case, again, with time machine. This information, of course, on the switch, there's not much you can do in terms of analytics and time series processing. So we actually export this information into a time series database based on Elastic, where you can do all your analytics alerting, analytics, and post-analysis of application performance, right? So this is actually also part of the demo we have at the booth. So not only visibility into how the containerized application is distributed through the physical fabric, but you can actually look at the specific traffic pattern as seen from the network between among all the containers and the east-west traffic. In summary, so we're really trying to leverage here a switch fabric to accelerate and improve the ability to root cause application performance issues and application availability issues in a Kubernetes environment. We're using OCP switches and an SDN control plane. I'm emphasizing the SDN control plane is because you need to have end-to-end visibility. If you do it with a regular switch operating system, you need to have some level of intelligence built on top of it to be able to correlate the information across the entire fabric. Because we have this built-in SDN control plane, this actually is a capability that comes natively out of the OCP switch running the Pluribus software. So visibility end-to-end across all the endpoints and the traffic flows. All you have to do is to subscribe with, it's a simple command, we call it a service. It's a Kubernetes connection service. You point it to the Kubernetes API server by loading the same API manifest required by all the nodes of the fabric, the Kubernetes cluster. And the goal here, again, is to rapidly correlate performance and availability issues for distributed applications. No agents required, so this is very important. This doesn't work for OpenShift or Rancher or any specific Kubernetes application. It works for all of them, right? Because we're not changing or touching the server. We're just subscribing to a standard API from Kubernetes, which is the same across all the vendors providing Kubernetes distribution. So again, no agents required, no special codes touching the server, all done from the network. And also, again, we implemented this powerful time machine. We leveraged the SSDs built onto these modern switches. And this is actually, particularly for Kubernetes, very important because in Kubernetes, when you are detecting a problem, it's always too late. The pods or the endpoint may be gone for good. And Kubernetes may have created more pods, more endpoints somewhere else. So ability to preserve memory and trace state of Kubernetes application, at least within a reasonable amount of time on the switch, is actually a key characteristic as well. A couple of minutes. I'm going to mention that, of course, this is an OCP show. So definitely, we have 11 OCP-based platforms this is running on. We have also partnership with IT Renew, and we run on the Wedge 100 switches built by Facebook as well. You can actually visit the OCP marketplace and get a lot more information on those solutions we support. And I'm going to spend like maybe the last 30 seconds, 40 seconds on summarizing who we are, what we do. So we build an open network operating system for OCP platforms and OCP switches. And on top of this operating system, we integrate an SDN fabric. The goal of the fabric is really to abstract the physical network and provide a very simple cloud-like programming model with all the centralized properties and object abstraction you have in a public cloud like, for example, Google or AWS. So same philosophy, but applied to on-prem networking. We have partnership in the OCP space with EdgeCore and Sesame or by IT Renew. And we also have partnership with Ericsson, Dell, Broadcom, NVIDIA, and also VMware, because we have integration also with VMware infrastructure. Our fabric can run across multiple topologies, fully distributed. There are no controllers. Is like a distributed database cluster, which can adapt to any topology, whether it's the leaf and spine I've shown you before, it's a multi-data center with the disaster recovery application, or it's a fully distributed cloud across multiple sites. Right? If you want to learn more and see a demo of what I've shown you today, because it's not just a science project, it's a real product, you can come to booth A26. I have 14 seconds, happy to take questions, either here or right after the presentation.
Can you get up to the microphone there? And then when you speak, can you take your mask off? It's really hard to sometimes hear.
Hello?
Yep.
Yeah.
Perfect.
So just quick question about the Kubernetes. So you have to, do you need to configure the subscription service on every top of the rack? How do you configure it?
Yeah, so you designate one of the nodes of the fabric. You may have, like in this picture, for example, up here, I have 6 nodes, right? You designate 1 or 2 nodes to speak to the Kubernetes API server on behalf of the rest of the fabric. You don't need every node to talk to it, only 1 node. And then because all these nodes are joined into this fabric, SDN fabric, we really have this information accessible from every node. So really, it's very simple. You issue 1 command on one of the switches designated by the administrator, and off you go. It's really a single command.